Equilibrium. Up until now, most of the reactions that we've considered, we have our reactants, we draw an arrow, and we have products. Looks something like this. Okay, so very straightforward. We have reactants, they do their thing, we get products, boom, done. Well, not all systems work that way. Some systems work like this, where instead of a single arrow, I'm going to draw a double-headed arrow. Okay, which means that the reaction is what we call reversible. It can go in both directions. All right, so one of those has a regular old arrow, the other one has that double-headed arrow. So we have this concept now where we have some reactions that are reversible, some reactions that are irreversible. So what do those terms exactly mean? So a reversible reaction is a reaction that can occur in both the forward and the reverse direction. Okay, and again, we use those double-headed arrows to denote our reversible reactions. So I have reactants, and I can go both ways. Okay, whereas an irreversible reaction can only go in one direction. So this will be a reaction that proceeds only in the forward direction. Okay, and that's where we use the single-headed arrow. So I have my reactants, go to products. Okay? Now, equilibrium is established when we're no longer forming more reactants or products at all. Okay, so equilibrium, it's reached when the concentration of reactants and products remains constant. Okay, and so basically what's happening is the reaction proceeds toward products at a certain rate. It takes, a certain amount of time to make our products. As the products bounce into each other and reform reactants, it takes a certain amount of time to do that. And so there's a rate of the forward reaction and there's a rate of the reverse reaction. So again, we have our reactants, going to products. All right, so that top arrow is the rate of my forward, and that bottom arrow is the rate of my reverse. Okay, and so equilibrium is established when the rate of the forward equals the rate of the reverse. All right, so we're no longer forming any appreciable amount of either of those. The rate is equal and we have a constant amount of concentration. Okay, so what this means is that the concentrations of reactants and products no longer changes with time. I can spell. Okay, so equilibrium does not mean the concentrations are equal, okay? see here. And so let me put it this way. Are not equal to products. Okay, so equilibrium does not mean that the concentrations are equal. It just means that the concentrations have reached a point where they are no longer changing. The rate to form one is equal to the rate to form the other. Okay. All right, so we can look at a dynamic equilibrium system. Okay, so I've got, let's see here, put down here. Got this dinitrogen tetroxide. It's a gas and it's colorless. Okay. And over time, it will establish an equilibrium with its product, nitrogen dioxide, which is also a gas, but it is brown. Okay, so over time, you can see it starts to get darker, until a certain point where that no longer changes. So if you look at those last two pictures, all right, equilibrium has been established because the brown color doesn't change between the two. And as you can see, we've got 5 of the product molecules in the third picture and 5 of the product molecules in the last picture. And so at this point, equilibrium has been reached. Okay, because those concentrations are no longer changing. All right, it's reached the maximum ratio of the two of them together. And that's what this all comes down to, is that we're going to see that there's something called an equilibrium constant. And so there's a ratio of our two components together. So we'll talk more about this, but I'll show you briefly right now. Our equilibrium constant is K. And so it looks like this. We're going to take our products over our reactants. Okay. So for this particular one, it's going to look like this. There's a coefficient of 2 in front of the nitrogen dioxide, so I raise that to the power of 2. Okay. And so there's a ratio there. Every single reaction that's reversible, that reaches an equilibrium, has its own unique equilibrium constant. And it is this ratio of the products to the reactants. And so once we've reached that ratio, it doesn't change anymore, unless we do something on purpose. Okay? Now what's interesting about these is because we're trying to get to that equilibrium constant ratio, this can happen. So in my picture A there, we started with all reactant. Okay, so in A, we have our start, all reactant. And in B, our start, if you look at that, what did we start with? Did we start with the reactant or did we start with the product? We started with all product. Okay, and over time, we're still going to reach that equilibrium. All right, this system still wants to get to that ratio of those components together. And so it doesn't matter. You can start with all reactants. You can start with all products. You can start an equilibrium system with a mixture of reactants and products, and it will always reach equilibrium. Okay. All right, here's just another one to look at. Over time, eventually, it will reach equilibrium. Okay, and so we have, this one is some hydrogen gas plus some iodine gas, giving us hydrogen iodide. Okay, and so you can see here, the equilibrium's been reached, because if you look at pictures C and D, if you count these particles in both pictures C and D, there's 8 of them. All right, and so equilibrium has been reached because the rate of the forward is equal to the rate of the reverse. So those concentrations aren't going to change anymore. Okay, so that is the basics behind equilibrium. Now there's a whole lot more to explore with it, but that's the basic understanding to start this off with. The foundation that we need is to understand that we have reactions that are reversible. We don't always just form products. We can reform reactants as well. And so every reaction that reaches an equilibrium is going to have its own unique ratio of those together and will adjust itself as needed to make sure that we get to that ratio.